In Maybad, in the Iranian province of Yazd, a rectangular pond covers 416 square meters. On winter evenings, it was filled with 10 centimeters of water, and by dawn, that water was ice. No refrigerant, no compressor, no thermometer, no notion that heat was a form of energy at all. And still the pit beside that pond swallowed 200 cubic meters of ice every winter. The place receives less than 100 millimeters of rain a year. That shallow pond is the ancestor of every cold thing in your house, and every cold thing around you on the street outside. The obvious question is how people endured the desert heat, and the answer to that one is dull, a matter of shade and darkness and water and patience. The real question is harder, and it changes what the machine humming in your kitchen actually is. It is how you make one thing colder than everything touching it, when you own no source of cold and no way to push heat uphill. Nothing in a desert is colder than a desert. The heat had to go somewhere. That somewhere was not the desert. It was not anywhere on this planet. Shade does not make anything cold. Shade removes the sun, and removing the sun brings a body down to the temperature of the air around it, and there the descent stops. That line is the ceiling of everything a person could build without understanding heat. In the desert, the line sits in a terrible place. On the 10th of July, 1913, a thermometer at Furnace Creek in Death Valley read 56.7 degrees, still the highest air temperature ever accepted anywhere on Earth. Satellite instruments aimed at the ground itself find worse. The surface of the Lut Desert in Iran and the surface of the Sonoran Desert on the Mexican border have both reached 80.8 degrees. That is the skin of the world people crossed barefoot and in thin leather. Night was the escape everyone reached for, and night was not reliable. On one July night in 2012, Death Valley never fell below 41.7 degrees. The air stayed above blood heat. Under those conditions, a shaded body is not resting. It is heated from every direction at once, and it has exactly one way out. The only way out runs through water. Sweat leaves the skin, carries heat away with it, and holds the core near 37 degrees, which is the only temperature the machinery of a human being will run at. The bill is enormous. When physiologists measured 91 men through ordinary military work in the desert, the average loss was 4.1 liters of sweat every 24 hours. Individual figures in that study ran from 1 liter a day to 11. Hard labor and heat costs about a liter an hour on its own. So the desert charged a price payable in the one substance the desert does not have. Food spoiled in a day. Milk in a clay jar spoiled faster than that. Water drawn from a well arrived warm and stayed warm. Grain, meat, and medicine had a shelf life measured against a single afternoon. And every remedy ended at the same line, because shade and walls and cloth and depth bring a thing down to the temperature of the air, and no further. Nothing was invented at this point, because the mechanism was already running in tens of thousands of kitchens. A clay pot fired below the temperature that seals its surface stays slightly porous. Water inside it does not sit still. It creeps outward through microscopic channels in the wall until it reaches the outer face, where the dry air is waiting. There it evaporates. Every molecule that leaves carries a fixed quantity of energy away, and that energy comes out of the water still inside. Measured in modern laboratories, a vessel of this kind holds its contents somewhere between 5 and 20 degrees below the surrounding air. It has no moving parts and burns no fuel. The same physics had been demonstrating itself on human skin since long before there were pots to fire. A body sweating in the shade and a jar sweating on a shelf are running one process. So the line drawn a moment ago was being crossed every summer day in ordinary houses by people who owned nothing else. People knew. They filled these jars on purpose, set them in the doorway where the wind ran, and drank cool water in a place that had none. What they could not do was keep any of it. The effect is small, it is self-limiting, and it dies the moment the pot runs dry. It cools only the thing already inside it. A cellar full of these jars is still a cellar at desert temperature. It cannot be stored, moved, banked, or spent later. And the visible sign of it looks like a fault, because a pot that cools is a pot that sweats, and a pot that sweats is a pot losing water. In a world where water is the currency of survival, that reading was not unreasonable. The cold was in their hands every hour, and it could never be more than a mouthful at a time. The second solution was overhead every clear night, and it was further out of reach than the first. Desert people knew the sky did something. They knew that a cloudless night runs colder than a cloudy one. They knew that frost forms on open ground and not beneath a roof. They knew that a man sleeping in the open wakes cold, while a man under an awning does not. All of that is one effect, observed 1,000 times, and never once assembled into a mechanism anyone could operate on purpose. The sky was weather, and weather was something that happened to people rather than a resource people used. There was one form of cold a person could actually possess, and it deepens the problem instead of solving it. Cold could be carried. Ice and packed snow exist in mountains, and mountains can be reached by donkey and by cart. Secondary accounts of the Royal Archive at Mari describe an ice house built around 1780, before the Common Era for a king in northern Mesopotamia, and record that no king before him had built one. Archaeologists have found ice pits in China from the 7th century before the Common Era, and written references point earlier still. Every one of these is transport. None of it is manufacture. The ice was harvested somewhere colder, hauled somewhere hotter, and spent. Nothing in that chain makes cold, and every link costs animals and men and time, which is why the ration went to palaces and not to households. So the position at the end of this stage is exact. Cooling that works and cannot be kept, sitting in every kitchen. Cooling that can be kept and cannot be made, sitting in a palace cellar. And overhead, every clear night, the largest cold thing in the world, with nobody yet able to spend a single degree of it. Put a number on the cold that a desert winter actually supplies, and the size of the problem stops being a matter of opinion. Climatologists count, for every day of a year, how many degrees the daily mean sits below freezing, and add all of those numbers together. The total is called freezing degree days. It is the closest thing anyone has to a measure of how much cold a climate hands out for free. A typical Yazd year has 20. That figure deserves a moment of your attention, because everything else in this story is built directly on top of it. There is an empirical model of thin ice growth on open fresh water, built from field measurements. Freezing degree days is effectively its only input. Fed 20, it returns 70 millimeters of ice over an entire winter, 7 centimeters. Spread across a pond of 416 square meters, 70 millimeters comes to under 30 cubic meters of ice. The pit waiting beside that pond holds about 200. The air alone falls short by a factor of 7. That gap does not close by working harder or by starting earlier. The shortfall is a toll charged by the water itself. Taking 1 kilogram of water across a change of state costs about 2.4 million joules, roughly 600 times the energy needed to warm that same kilogram by 1 degree. Water resists changing what it is far more stubbornly than it resists getting warmer. That is why the pot on the shelf cools so gently, empties so slowly, and never chills anything but itself. It is also why 20 freezing degree days buy so little ice. There is a second number in this problem, and it belongs to the human body rather than to the pond. Physiologists put young, healthy adults in controlled chambers, set them to light activity, and raise the load until the body could no longer hold its core steady. Across 6 protocols, the average threshold sat at 30.55 degrees on the wet bulb scale, which measures how much more water the air will still accept. In hotter and drier chambers, the threshold fell further still. That is the real shape of the wall in this story. The limit was never the temperature of the air. The limit was the appetite of the air for water, and every method the desert offered drew on that single account. Sweat spends it. The clay jar spends it. A wet reed mat in a doorway spends it. And when the account empties, they all stop together. 20 freezing degree days will not fill a pit. A liter of sweat will not outlast an afternoon. What this problem required was not a better way to spend the air, but a second place to send the heat. That place had to be colder than the desert, and nothing in a desert is. What finally broke the deadlock was not built to break it, and none of the 3 pieces involved were built for each other. Start underground. People on the Iranian plateau had spent centuries on a different problem. Because water sat in gravel at the heads of valleys and open canals lost most of it to the sun. The answer was to move water without ever letting it see daylight. A gently sloping tunnel is driven from the settlement back into the water-bearing gravel, and vertical shafts are sunk down to it for digging and for air. Gravity does the rest. The system is called a Qanat, or a Qadis in Persian, and it moves water by slope alone. Iran holds more than 37,000 of them. The oldest, at Gonabad, dates from the 3rd or 4th century before the Common Era. Its main branch runs 13 kilometers, drops 222 shafts along the way, and begins at a mother well 200 meters deep. 2,000 households still hold shares in that water. None of it was about cold. It was about losing as little as possible between the aquifer and the field. The second piece was the brick. Mud brick and adobe were chosen because the ground supplies them, and because a wall has to stand up. Their thermal behavior was a side effect nobody was shopping for, and it can be measured. Adobe conducts heat at about 0.6 watts per meter per degree, roughly 6 times faster than dry thatch. It also carries 1,700 kilograms in every cubic meter. That mass is what matters, because a wall that heavy takes most of a day to carry a temperature change from one face to the other. The third piece was a wall built to cast a shadow. Winter sun in central Iran sits low, and a pond left open to it gains back through the day what it lost overnight. So a screen was raised on the sunward side to keep that low sun off the water. Put the three together, and the accident becomes available. Water arriving through a Qanat is run out after dark into a shallow basin 10 centimeters deep, screened from the sun and open to the entire sky. By morning there is ice on it, on nights when the air barely went below freezing. A British account written at Shiraz in 1891 sets the routine down. A few inches of still clear water are let in, and by morning it is frozen. At night more water is admitted, and another inch or two is made. When the sheet reaches 3 to 6 inches, it is broken up and stored on the spot. The process repeats through the short winter until the storehouses are full. No name attaches to it. There is no inventor, no workshop, and no moment of insight in any record. The sequence just described is the most defensible reconstruction available, assembled from the physics of the surviving structures and from accounts by outsiders who watched the work. What the record does show is a procedure that worked, operated by people who could not have said where the heat was going. Here is the anomaly, stated as precisely as it can be stated. A shallow sheet of water is lying in the open. The air above it is above freezing. The ground beneath it is warmer than the air. There is no wind of consequence and no machine anywhere on the site. And the water is getting colder than everything it touches. That is the whole event. It is easy to read past that sentence without registering what it forbids. Heat moves from warmer to cooler, always, and it has never once been observed doing otherwise. For the pond to cool, heat has to leave it and arrive somewhere colder. The air is not colder, the ground is not colder, and the shade wall is not colder. Nothing on that site is colder than the pond, and the pond keeps cooling anyway. Modern instruments confirm the effect without any of the ancient staging. Put an open tray of water outdoors on a clear, dry night, shield it from the wind, and its surface will settle several degrees below the air temperature and stay there until dawn. The reading is stable, repeatable, and it does not care whether anyone understands it. The same thing happens in ordinary places. Grass takes frost on nights when the recorded air temperature never fell below 2 or 3 degrees, because the recording is made inside a shelter and the grass is not. Car windscreens ice over, while the road beside them stays clear, and none of these are rare events confined to deserts. They are the same process running at low intensity, everywhere, every clear night, in front of everyone. Something is removing energy from that water at a steady rate. There are exactly 2 candidates, and the smaller one is the one everybody already knew about. The smaller mechanism is the one from the clay pot, scaled up and laid flat. Water at any temperature is a crowd of molecules moving at different speeds, and the fastest ones at the surface occasionally carry enough energy to break free and leave as vapor. What stays behind is the slower crowd, and a slower crowd is by definition a colder one. The energy those escapees take with them has a name and a price. The price is called the latent heat of vaporization, and it is the energy a substance absorbs to change state while its temperature does not move at all. For water, it runs to about 2.4 million joules for every kilogram that leaves. That is the number met earlier, working in the opposite direction. In the barrier, it looked like an obstacle. Here it is the engine. Every kilogram that evaporates off a pond carries away 2.4 million joules that came out of the water underneath. In the modeled winter at Maybod, evaporation was pulling about 20 watts off every square meter of pond through the coldest nights. 20 watts per square meter is not dramatic and does not need to be, because it runs for 11 hours and never stops to rest. The people operating the pond had no term for any of this. The measurement did not exist yet. In December of 1761, a Scottish physician named Joseph Black finally established that a substance absorbs heat while changing state without changing temperature. 3 years later, he and a student measured the same quantity for steam. They got it wrong. Black put the figure at 750, then revised it to 810, against a true value of about 967 in his own units. So the sequence runs like this. The pond had been making ice for centuries. The first man to measure Y underestimated the answer by 16%. Evaporation accounts for 20 watts. The pond is losing far more than that. So where is the rest of it going? The answer is the reason this story is worth telling. It is going to space. Everything warmer than absolute zero radiates, and at the temperatures found on the surface of this planet, that radiation comes out in the infrared, peaking around 10 micrometers in wavelength. The atmosphere absorbs most infrared and sends it back down. It does not absorb all of it. Between roughly 8 and 13 micrometers, there is a band where dry air is close to transparent, and radiation in that band passes through the whole depth of the sky and does not come back. Specialists call it the atmospheric window. What lies on the far side of that window is the background of space, sitting at about 3 degrees above absolute zero. That is the destination the barrier demanded, and it was never on this planet at all. The pond was not being cooled by the desert. The pond was radiating into the coldest thing there is. Through a gap in the air that lines up almost exactly with the wavelengths a cool object emits most strongly. The modeled numbers for Maybod put it plainly. Through the coldest nights, the pond lost about 60 watts from every square meter by radiation to the sky. Evaporation took 20, and convection to the air took 1. The ground underneath handed 8 watts back. Radiation is not a contributing factor in this system. Radiation is the system, and everything else is a rounding error or a leak. That balance sheet is worth holding in your head, because it rewrites what the whole structure was for. Every design choice on that site serves one purpose, which is to keep the water pointed at the open sky and shielded from everything else. The window only opens in dry air. Water vapor is the strongest absorber in that band, and every gram of it overhead closes the gap a little further. On a humid night, the sky radiates almost as much down as the ground radiates up, and the net loss collapses. On a cloudy night, it closes completely, because cloud is opaque in the infrared and throws the ground's own heat straight back at it. This is why the effect belongs to deserts and not to river valleys, and why the climate that made cold impossible to buy is the same climate that made it possible to make. Modern laboratories have taken the same physics as far as it goes. A simple surface radiating across the whole infrared spectrum, facing a clear night sky, settles about 6 to 8 degrees below the surrounding air, and no further. Surfaces engineered to emit strongly inside the window, and almost nothing outside it do far better. Measured drops of 42 degrees below ambient have been reported, and the theoretical ceiling, with every parasitic heat path removed, runs to about 60. None of that was available in the 17th century, where the whole apparatus was a shallow basin, a shade wall, and the habit of filling the basin after dark. The distance between those two sets of numbers is 400 years of physics and nothing else. The advantage the laboratory has is not a better sky. The pond at Maybod and a nanophotonic emitter in a modern laboratory are running one process at different efficiencies. One of them was built by people who had a word for ice and no word for radiation. They had the geometry right without the theory, because the geometry is what the sky rewards. Point the water up, keep the sun off it, spread it thin, and wait. That is a refrigerator. The Iranian version did something none of the others attempted, which was to move cold across the calendar. Everything so far cools a thing while the cooling is happening. The pond and the pit together cool a town in July, using a night in January. The numbers for Maybod have been reconstructed by building physicists working from the surviving structures and a long run of local weather data. The pond covers 416 square meters and takes 10 centimeters of water at a time. On the best nights, it yields 12 millimeters of ice. Across a whole winter, the model gives about 120 millimeters in total, which is 49 cubic meters. Expressed as cooling capacity rather than volume, that is 4.3 megawatt-hours locked in a hole in the ground. Then the hard part starts. Ice in a desert has to survive from February to August with no power at all. The store is roughly 200 cubic meters, sunk below grade, packed with straw or thatch. Descriptions of the practice put the insulating layer over the top of the ice pack at 1 to 2 meters thick. The modeling shows why. With half a meter of thatch, about a fifth of the stored ice is lost over the season. Double the thatch to a full meter and the loss falls to 13%. The model also traces where the heat gets in. 15% arrives through the floor, 15% through the sides, and 60% comes down through the top from the dome above. That explains the dome. The dome is not decoration, and it is not a tomb. It is the lid on the leak. The same city solved a different half of the problem, and it did so in the air rather than in the water. Ice cools what it touches. A house needs the air itself to move and to arrive cooler than it left. The answer across the Iranian plateau was a tower on the roof, open at the top, divided inside into shafts. The Persian word is badgir, which translates as wind catcher. On a windy day, the tower takes air in on the windward face and pushes it down into the rooms below. On a still day, it works in reverse. Because the tower shaft heats in the sun, the air inside rises, and the building is pulled empty from underneath. Either way, there is a current, and it can be run over water on the way through. Yazd has around 700 of these towers standing. The oldest of them dates from the 14th century. The tallest anywhere rises 33.35 meters above the roof of the garden pavilion it serves. That is the height of a 10-story building, made of mud brick, for the sole purpose of moving air. The city was listed as a World Heritage Site in 2017. What makes the badger a separate branch of the family is that it never stores anything. It has no reservoir, no season, and no stock to run down. It is a machine with no moving parts that runs whenever the sun is up or the wind is blowing, which in that place is nearly always. The ice house banks cold and spends it. The tower never has any, and moves the heat anyway. Move west and the same physics arrives in an object small enough to carry. The porous vessel is the most widely distributed cooling device in human history, and almost nobody counts it as a device at all. In Egypt and Sudan, it is a zir or a kula. In Spain, it is a botijo. South Asia has the same family under other names. The engineering decision inside it is invisible unless somebody points it out. Clay fired hot enough vitrifies, meaning the surface fuses and the wall becomes watertight. These vessels are fired deliberately below that point. The wall is left slightly open so water can work its way through to the outside and evaporate off the skin of the pot. A potter who does that is choosing to lose water on purpose in order to gain something else. The device and the container are the same object, which is why it never looked like technology. Nobody patents a jar. There is a second version that goes further. A smaller vessel is set inside a larger one, and the gap between them is packed with wet sand. The inner chamber never gets damp. The sand keeps the outer wall saturated, and the food inside sits in a cavity held below the temperature of the room. Everything about this branch is the opposite of the ice house. It costs nothing, it belongs to everyone, and it needs no season, no labor gang, and no patron. It also cannot be scaled. 1,000 of these in a warehouse is still a warm warehouse containing 1,000 slightly cool jars. The technique that spread the furthest is the one that could never grow. The fourth branch cools nothing at all, because it works on the person instead. Desert clothing looks wrong to anyone who has been told that dark colors absorb heat. Across Sinai and the Negev, the robes are frequently black. In 1980, a team of physiologists tested the question directly, in the field, in the Rift Valley between the Dead Sea and the Gulf of Aqaba. A volunteer stood facing the sun at midday, in air ranging from 35 to 46 degrees, in half-hour sessions. He wore 4 configurations in turn: a black Bedouin robe, a white robe of the same cut, a tan army uniform, and shorts. The researchers measured radiation gained, heat lost by convection, heat lost by evaporation, heat stored, and heat produced by his own metabolism. The black robe absorbed 2.5 times as much solar radiation as the white one, and 1.5 times as much as the uniform. The total heat gained by the man inside was the same in every case, every configuration. Color did not matter. The extra energy the black cloth took in was shed before it ever reached his skin. The proposed explanation is that the loose robe works as a chimney. Cloth heated on the outside warms the air in the gap. That air rises and escapes at the neck, and cooler air is drawn in at the hem. The garment is not insulation, and it is not a shade. It is a ventilation duct with a person inside it, and it runs on exactly the account the barrier described, because what leaves at the neck is warm air loaded with the wearer's evaporated sweat. Set the 4 branches on a map, and the pattern that appears is not a cultural one. A survey of the surviving Iranian ice houses counts 129 still standing, and they are not distributed by dynasty, by trade route, or by language. They sit where the winter climate allows ice to form on site, or where mountains stand close enough that ice could be hauled in and stored. The boundary is drawn by the sky, and where the air overhead is dry and the nights are clear, the window opens and the pond fills. Where the air is loaded with vapor, the window shuts, and no amount of skill reopens it. The evaporative branch runs into a matching wall. Its performance depends on moving air to carry vapor away from a wet surface. An analysis of global wind data found that 98% of the world's population lives, at any given moment, in air moving slower than 4 meters per second. Still air is a poor customer for evaporation. So 2 constraints sort the world into places where cold could be made and places where it could only be bought. This is the point at which the story stops being about invention. 4 separate traditions, working in different centuries with different materials and no shared vocabulary, arrived at 4 devices that exploit the same 2 exits. There is no diffusion to trace and no first inventor to credit. There is a planet with a gap in its atmosphere and a liquid with an expensive change of state, and every culture that stood in dry air long enough found one or both. These systems were still in ordinary working use in Iran as recently as the 1960s. What replaced them changed nothing physical. It changed who was allowed to have it. Once cold can be stored, it becomes property. That single change did more to reshape the places it reached than any of the devices themselves. A pot of cool water is a private comfort that ends when the pot ends. A pit holding 200 cubic meters of ice is a stock, and a stock has an owner, a price, a guard, and a season of scarcity. Cold stopped being weather and became a line in an account book. The people who held it could keep food, sell it out of season, and hold a reserve against the worst months. Ice enters the records like grain. An English traveler in Persia in the late 17th century reported that cooling drinks and food with ice was ordinary practice rather than a court luxury. The infrastructure underneath it lasted in a way that is hard to overstate. 3 of the 5 watermills fed by the Gonabad system were still turning in 1966. Then the whole arrangement was replaced, in about 1 human lifetime, by a machine that does the identical job with a compressor and a wall socket. Now consider the scale. Cooling now consumes more than 2,000 terawatt-hours of electricity every year. That is 2.5 times the total electricity used by the continent of Africa. It is close to 1/10 of all the electricity generated on this planet, and about 1/5 of the electricity used inside buildings. There are roughly 1.6 billion air conditioners installed. Projections put the figure at 5.6 billion by 2050. That works out at around 10 units sold every second, continuously, for 30 years. Every one of them does what the pond did. It finds somewhere colder to put the heat. The difference is that the pond used the sky and asked for nothing, and the machine uses a coil, a refrigerant, and a power station. Who is allowed to have it is now the whole question. About 3.5 billion people live in regions with high temperatures. Around 15% of them own an air conditioner. The other 85% are running the older system, which is sweat, shade, still air, and whatever the night gives back. That system has a hard failure point, and it is worth your attention. because the failure is not heat stroke in the loose sense. The body loses heat to the air by evaporating water off the skin. That transfer only happens if the air will accept more water. As the air fills, the evaporation rate falls, and the heat produced by simply being alive stops finding an exit. At that point, core temperature begins to rise, and no amount of rest, shade, or drinking will stop it. Physiologists call this condition uncompensable heat stress, meaning the body can no longer balance the heat it gains against the heat it is able to shed. It does not require record temperatures. It requires the wrong combination of heat and humidity, held long enough. None of it is exotic. It happens in apartment blocks, in fields, and in delivery vans. The accounting is now reasonably firm. Between 2012 and 2021, heat was associated with an average of 546,000 deaths a year. In 2024 alone, heat exposure cost an estimated 639 billion hours of potential labor. The lost income attached to those hours comes to about $1.09 trillion. Both of those figures are the highest on record. Those numbers are the price of the same problem the pond was built to solve, unsolved, at a population of 8 billion. The technology exists. It has existed since a shallow basin in Yazd froze overnight. What has never existed is a version of it that everyone can run. 3 claims travel with this story that do not survive contact with the sources. The first is the figure of 35 degrees on the wet bulb scale, widely repeated as the limit of human survivability. It was a theoretical estimate, derived from physiological principles and never tested against people until 2021. When it was tested, across 6 protocols, no subject reached it, and the average threshold sat almost 5 degrees lower. The real limit is worse than the famous one, and it moves depending on how dry the air is. The second is the black robe. The 1980 measurements are solid, and the conclusion that color made no difference to the wearer's heat gain has held ever since. The explanation has not. The chimney account was proposed rather than demonstrated. A critic writing in New Scientist objected that the neck openings are too small for the effect described, and noted that Bedouins often wear white when crossing open desert. The finding stands, and the mechanism is still open. The third is the icehouse itself. Popular accounts date these structures to 400 years before the Common Era, and describe them as machines that froze water and air that never went below zero. The best studied of them, at Maybad, is reported to be about 400 years old. Many ice houses across Iran never made ice at all, and simply stored what was carried down from the mountains. And the winter air in Yazd does drop below freezing, for the 20 freezing degree days counted earlier. The truth is better. Radiation and evaporation pulled the pond below the air temperature, which stretched a freezing season the air alone could not have supplied. 2 things remain genuinely unsettled, and they belong in the account. The ice yields do not balance. One survey put annual production at an Iranian pond at 100 centimeters of ice. The modeling team who reviewed that figure judged it far too high, and predicted 12. Their own answer then filled only a quarter of the store it was supposed to fill, and they listed 4 possible reasons, one of which was that their model is wrong. That is an honest number. The second unsettled thing is the date on the discovery. The first laboratory demonstration of artificial cold by evaporation is credited to William Cullen and reported variously as 1748, 1755, and 1756. The paper is dated 1756, and everything earlier than that is inference, which is the correct posture for all of it, including everything you have just been told. Look at the room around you. Somewhere in it, or one wall away, there is a box that is colder inside than the air in the room. It is running right now, and it has been running all day. Open it, and the cold falls out at your feet, and the back of it is warm, because that is where the heat went. Everything in that box is edible tomorrow, because its heat was taken somewhere else. The milk that used to spoil in a day now lasts a fortnight. The air moving through the vent above you is breathable in August, because its heat was taken somewhere else. The glass in your hand has water beaded on the outside, because the air touching it gave up heat and could not hold its water anymore. That water was floating in the room a minute ago. The trains, the shops, the hospital wards, the server rooms holding everything anyone has ever typed, the vaccines, the blood, the semiconductors. None of those industries would exist without somewhere to put the heat. All of it is one operation repeated at scale. Find the heat and give it somewhere to go. None of that is a comparison. It is not a poetic link between two distant things. The machine in your kitchen and the basin at Maibad are not similar processes. They are the same process, with different hardware bolted to the front. The bill for turning water into vapor is still 2.4 million joules a kilogram, and it has not moved. The gap in the atmosphere between 8 and 13 micrometers is still open tonight, over the roof above you. It closes when cloud comes over and opens again when the sky clears. Every clear night, the ground under this whole planet is quietly bleeding heat into space through it, whether or not there is anyone underneath to use it. The only thing that changed is that people learned the name of the thing they had been using. The using came first. It came first by a very long way. Before the word radiation existed, before heat was understood to be a form of energy, before anyone had measured a joule, someone in a dry valley walked out after dark carrying water. They let it run out flat across a shallow floor, 10 centimeters deep, 400 square meters wide, screened from the low sun and open to the whole sky. Then they went to bed. The sky did the work while nobody watched it. They came back at first light with a tool to break it up. They did that every night of every winter, for as long as the winter lasted. Nobody wrote their name down, and nobody thought to. They could not have told you where the heat had gone. They knew it was gone. They knew the ice would be there in July, and they went out again the next night with more water.